in South Africa on the 21st of August. Now, those who remember the history of the 1960s, 21st of August was a significant date. So I had a bit of time before turning south in Oxford, so I went to London and was a tourist at that time. And one of the events that was on in London was a Soviet exhibition at the Commonwealth Institute. So I went along, intended to go to this exhibition. I found it surrounded by a crowd of demonstrators because on the 21st of August, as you will remember, the Soviet tanks rode into Prague. So Jan was on the train on the way home from holiday in Britain. He heard the news in Germany, he got off the train, took the train back in the other direction. So essentially, we arrived in Britain at the same time, and both perhaps not knowing what would happen, so somewhat unintentionally, we both stayed. So I didn't actually meet him for a couple of years because he finished his first year at Bristol and then came to Oxford. But it's amazing how even bad things like that can have the occasional good consequences. And it hadn't been for the Prague Spring, many of us, probably all of us, would not have got to the end of lives that have been brought. So, we came to Oxford in 1970, I think it was, to start this DPhil on the Economic Institute. I believe I understand internally examined when he wrote his thesis. I don't have a record of that, but I'm pretty sure that that is correct, because I can remember in some detail what was in his thesis, which would not have happened if I hadn't read it carefully at the time. Anyway, so here's another little event that happened. Later on in the 1970s, there was a meeting at the Isle of Thorns, the University of Sussex Conference Centre, and Peter, Jan and I decided it was a nice weather. We would walk from Oxford to the Isle of Thorns, some distance. We took 3.5 days about it, stopping in Westminster. So it was quite a substantial walk. But it was a lovely time, and I think really enjoyed that interlude. Then I will jump forward a bit. So in 2008, I was directing a program at the Isaac Newton Institute. The subject was combinatorics and statistical mechanics. Now, what do I know about statistical mechanics? The reason for this was that just before that, Alan Sokol had taken a half-time job at University College London. And I thought, this is a wonderful opportunity. We should exploit it in some way. How can we do that? We should get mathematicians and physicists together at the Isaac Newton Institute to study about things like that. And indeed, Alan was exactly the right person for that, because in the introductory workshop of that program, where we were trying to learn one another's language, so a mathematician would give a talk, and Alan would jump up and say, I should explain to the physicists that what he really means is blah, and vice versa, the other way around. So that really helped the communication. But the really nice thing about the mathematics is that Jan arranged for me to be a GC Stewart Fellow at King's. That was just marvelous in several ways. Gave me a feeling of belonging in Cambridge rather than just that somewhere. It allowed me to interact with the Keys undergraduates. So the beauties of the thesis are to give 3 or 4 lectures to the undergraduates. I gave 4, and those are the titles. 3 of them have literary references, which you may or may not spot. Well, I mentioned Alan Sokal, so that should make one of these to spot. The other thing was the person who just had an operation at the time, she was able to come to Cambridge, stay in the Keys flat and recuperate and actually do some very significant work in statistics while she was there. So it was a great time. I'm very grateful for that opportunity. But this is the well, actually, now I'll say it first. So in these lectures, it turned out that a number of fellows Keys made appearances, including John Benn, Donald Fisher, John Conway. My last day in Keys, the end of the program, it was the President's Garden Party. And those of you in the Association of Keys will know about this event. So we were at the President's Garden Party, and the master arrived and asked the President for permission to interrupt the garden party for the ceremony. The ceremony was to admit me as a member of the Keys. So I am a member of Keys College, the college for which these eminent people that I showed you on the last slide were fellows. I feel very proud of that. Very grateful to Jan for giving me this opportunity. This is my only formal connection with Cambridge. The master said to me at the time, now you'll start getting begging letters from us. But to their credit, I have not received a single begging letter in Keys. Maybe they just forgot. Unfortunately, this is the real thing that I regret. Jan was away on sabbatical for most of that year, and most of that 6 months. So we didn't actually have the opportunity to sit down and work together. I would have really appreciated some time to do that, but it wasn't to be. I had plenty else to do in that time, but working with Jan was not one of the things that happened. Okay, so these are my 4 joint papers with Jan, only 4. I'm not certainly not going to show this to you. The last paper on this is the one that showed the Sims conjecture, and indeed, as you see from the title of the paper, it does indeed have distance transitive graphs in it. We proved the Sims conjecture, and we were able to adapt the methods that Norman Briggs and Gerald Smith had used to show that as a consequence of the Sims conjecture, there are only finitely distance transitive graphs. The point is that the graph, you start off from the vertex and start walking out from it. The graph expands, you get more and more vertices for a while. Then at a certain point it stops expanding. The point where it stops expanding is at most the bound in the Sims conjecture, because you see it's a distance transitive graph, so the points at any given distance on the orbit of the vertex stabilizes. So the proof of the Sims conjecture bounds that number. So it grows for a while, then it can't grow anymore. So it might remain constant for a while. And the methods of Higgs and Smith allow one to prove, nobody had actually proved at that time, because they didn't see what use that is, that the number of steps it takes constant is bounded by the number of steps it took to reach that point where it becomes constant. So it's constant for a while, and then it shrinks down. And of course, the number of steps that shrink down is bounded by function of t as well. And so you have the result. So that's in that paper, along with the most important thing in this. So that's that. Everything about that is. So I have a long-standing obsession with the actual permutation with following set of unordered subsets of the domain, and the first and third papers there are related to that, and the third in particular has had various applications. Well, the second one as well, I suppose, that's true. But what came out of the second one was I have some joint papers for Gotsi Baba, and in fact, we have a very bad reputation. First thing we did together was in 1990. It didn't actually get published until about 2010. We were not good at writing them up and submitting them because essentially, Gotsi would always say, we can do better. And I would write it into an idea of pushing on it. But that tended to take a long time because we were both involved in other things too. Anyway, so we eventually published that paper. This was in the, no, not that one. So the next one that comes out, this was in the volume of the Journal of Algebra, in memory of Albert Serge. And finally, one is the Journal talked about it. So those are my papers with that. But what I'm not going to do is spend a lot of time talking about Young's mathematics. If I wanted to, if Young were here, what I would be doing is telling him about some new things that have come up and stuff I can do that I know would interest him, and I'm sure he would have something to contribute to. And so from now on, from the rest of my talk, I'm going to tell you about some new results, which are not such big deals, but in fact, probably interesting and probably worth a look for various people. So I want to talk about two particular things. First of all, this is a strengthening of the theorem of lambda from 1903. So, the theorem says that given the number of conjugacy classes in the group, there are only finite in the group. So, we had this, in a sense, let's talk this now, that the number of the order of the group is bounded by a bunch of conjugacy classes. And we have a strengthening of that theorem. We, in this case, are these authors. Patrick Banwell, Patrick Canton-Nath, Benjamin Sambawi, and me, which I want to tell you about. So, two Indian institutions on like this. So this is because what I spent a lot of time in the second half of the pandemic thus far doing was it started off with running a research discussion group led by Ambassador Kumar in Kochi in Kerala in South India. He saw a survey paper put on the archive with some results about graphs defined on the groups, and he invited me to lead this research discussion. This really gave me the impression of what big companies in this, because all sorts of people took part in this discussion and started proving theorems. A lot of stuff happened. You know, this, I think, was my lifetime. This kept me sane, and this stuff. Anyway, so here's a graph to find. You take one group, and you define a soluble conjugacy class graph. The vertices of the conjugacy classes, you join two classes C and D if there's some element in C and some element in D which generate a soluble group. Right? That's the soluble conjugacy class graph. The number of vertices of the soluble conjugacy class graph is the number of conjugacy classes. And Landau tells us that there are only 5 groups with different frequency classes. So there are only a finite number of groups with a different soluble frequency class graph. If you have a finite graph, its clique number is the size of the largest complete subset, the largest set of vertices where any pair are joined. So here's our theorem. Given a positive integer k, there are only finitely many finite groups whose soluble conjugacy class graph has clique number k. So Landau says the order of the group is bounded by a function of number of vertices of this graph. We say it's actually bounded by a function of clique number of the graph. So it is formally a straight line. Now, I don't think this is the result that's going to change the course of group theory, but on the other hand, it's quite cute with the result. And it's nice. We do this classification tendency for groups. Now, of course, this is something that many of us have thought about, including Jan, Joe, and Martin. Can you avoid using classification in functional problems? And mostly the answer is no, you don't hope of doing anything unless you use it. But in this case, so I'll give you a rough, very rough sketch of the group. So we start off with a graph where we, a group where the soluble conjugacy class graph has K. We want to bound it group. So first of all, there might be a soluble radical. Let's assume that we can prove the theorem of groups with soluble radical is true. Then it's not so very difficult to say, well, okay, that will do the job for the arbitrary group that we have in front of us. So without positive generality, we can assume the soluble radical is trivial. So the software is a direct product of non-coordinates groups. It's relatively easy to bound the number of these simple groups, and it's enough to prove the result just for one group with simple software, one almost simple group. And then, as I say, a light touch graph. There's one easy argument that deals with the alternate groups. There's an easy argument that deals with groups of V type of bounded rank. There's an easy argument that deals with groups of V type of bounded fields, and the sporadic groups is, of course, not a problem in a thing like this. So that's essentially all that we need. But on the other hand, if we didn't have classification, that argument would even get ground. So there are explicit bounds for Landau's theorem. We don't have explicit bounds in our theorem. We have not even tried to work out. So that is an open problem. Another open problem, of course, is in the soluble conjugacy class graph with the more potent conjugacy class graph too. Can we pin the graph down, which will reduce the clique number and still prove the result of this sort? So there are various open questions there. Anyway, so that's, I think, something that's quite cute. But so here is something else, and this is very much still work in progress. So this is a Peter Morgan story, but I hope that's okay. So when I arrived in Oxford in 1968, Peter was just finishing off a 50-odd page manuscript on permutation groups between 3 times the prime. This was extending what it was realized to do this twice the prime. And he said he gave me that paper, and that's what I went to work. Well, the paper was never published. I'm not exactly sure why. Olaf Tomaszka and Leonard Scott had proved similar things, Olaf in Berlin and Leonard at about the same time, and there was definitely a plan for Peter and Leonard to wrap this up jointly. And Leonard Scott has actually provided me with some of the historical material on that. But that they never did, and so this is here without trace. It was, I think, a paper that could be extremely influential in the sense of this was the time when combinatorial methods were really coming into the study of permutation groups, graph theoretic methods, method space and association schemes and relations and all that kind of stuff. And Peter gave a wonderful explanation of what these methods were and how they could be used in a practical problem. Well, I noticed that there's no point trying to classify permutation groups now, because using a classification, you have much more general classifications like all but you can extract some combinatorial results out of this without the assumption that P is prime, without the assumption that there's any kind of automatism at all, purely combinatorial results. And so I had an undergraduate student reading these part of her summer research project to sort this out. And she's just about finished now, and we're in the process of writing up the paper, but she wanted something else to do. Well, fine, okay, so I invented this problem. You may find this amusing, perhaps. So permutation group properties often come in the hierarchy. You have transitive groups, quasi-primitive groups, primitive groups, and depending on your taste, you can go up from there. If you like synchronization, you can go up to synchronizing, separating, blah, blah, blah. And up at the top would be two transitive, let's say. Or there are other things, other routes up from primitive to two transitive. There are various properties. So I thought, if you have two properties P and Q, where Q is stronger than P, can you invent a property which is independent of P, that has the property that P together with that is equivalent to Q? In other words, a property that lifts P up to Q, but makes sense even in the absence of P. And I started off, I struck it lucky, the first example I tried to look at. Suppose P is quasi-primitivity and Q is primitivity. I'm sorry, the letters have got backwards. It should be the other way around. But never mind. This turns out to be very interesting. And so here's the property that we're going to use. So this is pre-primitive. A transitive permutation group is pre-primitive if every G-invariant partition is the orbital partition of some subgroup. So that's the property, right? Now suppose you have a permutation group which is pre-primitive and also quasi-primitive. Quasi-primitive means every normal subgroup is trivial or transitive. Right, well, I said...
It's omega is a set, not a group. So what does it mean, subgroup of omega?
Means I've made a typo, I'm sorry. Well spotted, so someone is still awake. Should be G, sorry. But the point is that let's the orbit partition of some subgroup. Let's the orbit partition of the normal subgroup. And so if the group is also quasi-primitive, this normal subgroup is transitive. And so the partition is trivial, so the group is primitive. So this does what I said. Pre-primitive plus quasi-primitive is equivalent to primitive. You can do other things in the hierarchy, but this is the one that I will tell you a bit about, because this is the one that has some results on. So here are a few of our results. And I just explained why a permutation group is primitive if and only if it is quasi-primitive and pre-primitive. So it does the job that I wanted it to do. Pre-primitivity goes upwards. A regular permutation exactly regular, is pre-primitive if and only if it is a Dedekind group. That is a group, all of whose subgroups are normal. And a Reith product of transitive groups in its imprimitive action is pre-primitive if and only if the two factors are pre-primitive. So that's nice. But you might say, well, what about the direct product in the product action? That's closely related. It fails for that, and you can see this now, because suppose you take two regular permutation groups. The direct product in the product action is also regular. So let's suppose you take, so if the two factors are pre-primitive, then they're Dedekind groups. And Dedekind groups, as you probably remember, are either abelian or else of the form Q cross A plus B, where Q is the quaternion group of order 8, A is the element within the 2 group, and B is a being group of odd order. So let's take Q8 and Q8. Q8 cross Q8 is not a dependent group, and therefore is not pre-primitive. So it fails for the direct product, but it fails for weak product. And we haven't really got to the bottom of that yet. But there are various other interesting group theoretic constructions that you can look at here. Anyway, that's as far as we've got. But we've looked at some others. We've looked at pre-synchronizing, which is the property which together with primitive is equal to synchronizing. We've even gone down in the hierarchy and looked at pre-quasi-primitive, the property that together with transitive is equivalent to quasi-primitive. So there are lots of things that you can do here. For an undergraduate fascinated by permutation groups and interested to work on this, actually I struck on a very good problem here. And you know, it is a problem. This is the sort of problem I think young people enjoy. So it's such a shame that you can't do it. But pre-synchronizing turns out to be not so interesting. Pre-synchronizing group is either primitive, in which case by definition synchronizing, or else it's kind of what four actually regularly. So there's not much else to it. But never mind, that's how things work out. And there may be other examples where you can use arguments like this. So my friendly idea that anyone is welcome to take a look and see what you can make of it. So I will now just finish. I don't want to keep people from lunch. I knew Jan for 50 years. I learned him a lot I think we needed to do. And so what I can say is, Title Jan, we're still here in this messy world. We can show you the best we can.
Is there some place where you have exposited this hierarchy of primitive and synchronizing? And I know you know what synchronizing is, but I promise you not everybody in this room does.
I know, I'm very much aware of that. I didn't want to take the time to define it. But yes, there is indeed. Joao Arijo and Ben Steinberg, and we have a 120-page paper in the EMS surveys a couple of years back that talks about all this stuff. And it is really intended to be an expository table. So that's the thing I recommend if you want to know synchronization. Synchronization is a property that implies primitive and is implied by two transitive or two genes. So it is in the book there. And I think it's a very interesting property. So I think I was just in the British Combinatorial Conference in Manchester, and there was quite a lot of talk there about the whole-page conjecture. The whole-page conjecture, which says that if you take the K type of group, that's a Latin square. Can you find a transversal, like it cells, one in each row, one in each column, one containing each entry? You can do that if you know the two subgroups of your group are either trivial or non-cyclic. And that result is used in groups of simple diagonal type, non-synchronized, as long as there's three factors in the soft. And so there's an interesting history there too. This was proved in 2009 using group methods by Jill Wilcox, Tony Evans, and John Bray. The first two papers appeared in the journal out that year. John never wrote up this until quite recently when I needed it for the synchronization project. So I went into his office and said, John, can you just write out that proof? He not only wrote it up, he redid the calculations, and he redid them in two different ways so that we could be pretty confident that the result was right. This was for J4. Quite a big group and has no small permutation representation, so it was quite a job. but he did it, and that's the time. So, yeah, synchronization. Yeah, so that probably answers your question. Yes.
So your definition of phase two. So you will say that that this is like the weakest ones among different ones that P and phase two will apply to.
Well, I'm not absolutely certain that, but I haven't done it in a really systematic way. I've just said, what property do we need to add to it? And so if you take close-out primitive, close-out primitive says that the normal subgroup is trivial or transitive. Primitive says every gene-varying partition is trivial. So to lift one to the other, you need every gene-varying partition to be the order partition of the normal subgroup. And I mean, I don't know quite what I would need to do to prove that that's the weakest way that we can achieve that, but it seems to me that that's, that pretty much does this. I haven't thought about that sort of question. With all of these things, so in fact, the one that lifts you from transitive to quasi primitive, Marina asked me about that. And I thought, and I wrote down the condition for doing, and then I saw that actually there's a weaker condition for all sorts. So it's not always obvious, but the condition that's in transitive quasi-primitive is that every orbit should have the property. So if you look at the group induced on any orbit, which would itself be quasi-primitive. In other words, any normal subgroup should either trivial on that orbit or should be transitive. Of course, if you have that property and the whole group is transitive, then it's quasi-primitive, no question. But that's the best I can do in that case. It doesn't seem entirely satisfactory, but that's what I decided.
Okay, let's thank Peter again. It's 2 o'clock, and it's some lunch upstairs.